Welcome back to Module 3, Part 2 of Neurofeedback Foundations. Let's dive right back in. So, as we said earlier, the brain is an electrochemical organ. In other words, it communicates signals from the brain to the body and from sensory organs in the body back to the brain and within itself via electricity and chemicals, many of which you've heard about, like adrenaline, noradrenaline, serotonin, dopamine, GABA, among others. Electricity is generated by ions, specifically positively charged sodium and potassium ions, in and around our cells. In the resting state, there is a higher concentration of sodium outside the cell and a higher concentration of potassium inside the cell, which means that inside of the cell is negatively charged as compared to the outside. When a neuron receives a message from another neuron, it opens voltage-gated sodium channels. As these charged atoms flow across the membrane, it changes the charge across the membrane, which is called depolarization. The more sodium that flows in, the more channels are opened until a certain threshold has been met, and it creates an action potential that excites the adjacent membrane, opening more channels as the electrical impulse travels down the axon to the end, like ripples on water. When the action potential reaches the end, called the synaptic junction, neurotransmitters are released. These neurotransmitters then cause opening of the sodium channels in the body of the next neuron, and so forth. So you can see here, there is a stimulus. Usually this would be some, we'll just say serotonin, that opens the voltage-gated channels. Sodium flows in until the threshold goes from -70 microvolts to -55, which then excites the membrane, multiple channels open, and then it flips them closed, which then causes repolarization, and it goes back to the resting state. This is representative of the myelin sheath, which is like insulation on our copper wires in our walls, which helps the electricity travel faster. And in fact, the electricity can jump from node to node. These are called nodes of Ranvier. Electricity can jump, which makes it much faster, get down to the end here. The myelin sheath is made up of Schwann cells, which you saw at the end of the last video. This is the cell body. These are dendrites, which receive information to the cell body. And these are the axon terminals. Now, this is really key to understanding why neurofeedback is so powerful and how it differs from medications. So if you need to rewind and listen to this over again, this is fine. This is the synaptic junction, also called the synaptic cleft, right here. This is where medications target the problems in our patients and clients. Most physicians might say something like, you probably aren't making enough serotonin. That's why I'm prescribing an SSRI. Okay. There are other medications that act at this point, at this cleft, like psychostimulants, Vyvanse, Concerta, Adderall, Ritalin, and antipsychotics, which target dopamine, gabapentin, etc. Now, neurofeedback specialists, on the other hand, believe that people have plenty of serotonin or whatever reuptake inhibitor they are prescribing or the patients have been prescribed. They believe that the problem is in the electricity, not in the synaptic cleft. So if you can see here on the left, this cell body has received a message. It's opened the sodium-gated channels, and there is an excitatory spark that's running down and then triggering an electrochemical event in the next or the receiving neuron. Okay. So just imagine if the electricity, if the spark is too wimpy here, or the action potential, then not enough neurotransmitters will be released here in the synaptic cleft. But what if there's too big of a spark or too much of a certain wavelength going through here? Then you're going to release too much neurotransmitter. So if we can train people to control their electricity, then they will impact the neurotransmitter release at the cleft. The best part is that instead of affecting the entire brain like medications do, QEEG guided neurofeedback is targeted and specific. So I would love for you to draw a picture of a synaptic cleft and an action potential and ion channels just like this, and label it to cement that into your memory. We'll see you for part 3.